This is geometry lessons 12.1 and 12.2. So we're mainly going to be focused on ratios and proportions, but 12.1 talks about some size transformations, which we've looked at before, and how the two are going to relate. So the big idea says size transformations and their images lead to figures in which corresponding lengths are in equal ratios. So where we're headed is similar figures, but right now we are going to focus just on the mechanics of ratios and proportions and how they relate to size transformations, meaning we shrink a shape or we enlarge it, and we're going to look at the ratio of the side lengths, what they look like. All right, so example number one. A size transformation has mapped the original triangle ABC to the image ABC. And remember, we look at that, we know the original doesn't have those special markings. The image has those special markings. We can call this A prime and B prime and C prime, or the image of A, the image of B. Either way, the vocabulary there is proper. So that size transformation has happened. I went from here to here. It's obviously gotten smaller. So I know that the magnitude of that is less than 1. So we're going to trace this. We're not actually going to do it. I've got it done for you. You're going to trace the triangles, and you're going to find the center and the magnitude of the size transformation. All right, so what does that mean? We've looked at these before, but maybe not specifically with the center, and we've talked about magnitude. So here's the solution. If you were going to actually physically do this, what you would do is you would draw a line from A through A prime, and then from either one, either C to C prime or B to B prime, as you can see has been done right here. And where those two lines cross, so if I drew the A's and I drew the B's, they're going to cross out here. That point where they cross, that is the center. And if I connected C and C prime, they're also going to hit in the same exact spot. That tells you that this size transformation was from this center out here, and we're going to call it O. If the shape was up here, the center would be out that direction. So a size transformation is always in a direction, all right, and it's from a center. You're just going to connect those lines, and it's right there. And then to determine the magnitude, if you don't actually have the side lengths here, of course you could measure them, right, and compare AB to the image of AB, AC to the image of AC. But I'm also going to be looking at the relationship from the original to this center and the image and this center. And so they've given you some measurements here. If you were doing this, they wanted you to actually draw it and measure it with a ruler, but I'm just going to give you these measurements. From O to B prime is 2.25, that measurement right there. And then from O to the original B, right here, is 4.5. And so we're going to go ahead and set up a ratio and compare those two. Okay, and they've got that set up here. If I'm going to compare the distance from O to B prime and the distance from O to B, I set up those measurements that I've taken there, simplify that fraction. You can do that in your calculator, and that actually is exactly 1/2. 2.25 is exactly half of 4.5. If I double it, I get 4.5. So that tells me that this size transformation was exactly 1/2. So this new shape right here, because I've measured these distances, is exactly half the size. All of these side lengths would be half. So if this original one was, let's pick a reasonable number here. Let's just say it was 4. I know that the new one would be 2 because I've measured these distances here, and I can tell that the ratio there is 1/2. So it's half the size. So just a quick review on size transformations. We're going to look at how do we set up these ratios and proportions to solve for some missing sides when we're given to these. All right, so real quick, the theorem, just so we're used to the notation again. When you see this big S with the little k, S means there was a size transformation, and k is the magnitude. So that would be like the 1/2 right here. If it's bigger than 1, that means it's enlarging. If it's a number between 0 and 1, like 1/2, it means it's getting smaller. It can also be a negative, and we're going to look at that down here. But a negative puts it on the opposite side of our center. So it could still, if it was like a negative 1/2, it would get smaller and it would end up on the other side of the center. And if it was a negative, say 2, or a negative number less than -1, absolute value bigger than 1, it would get larger and still end up on the other side. And we'll see that down here at the bottom again. All right, if you were given a coordinate with x and y, you would take that magnitude right there and you would multiply each of those by that. So if this was on a graph and it's a size transformation of 3, you would take each point x and y and times them by 3, and that's going to get you the new points right there. So this is all when k is not 0, right? Because if we multiplied by 0, it just goes away. It's just 0. So all numbers that are not 0, this will work out. Like I said, magnitude is k. And if this is on a graph, it's always going to be centered around 0, 0. But when we've got these other ones, we can, again, find that center by connecting these lines and seeing where they cross. A couple properties that we've talked about that don't change when you have a size change. They are preserved. So this is the size change preservation properties theorem. We talked about A, B, C, D. Notice there is no D here. We've got angle measure, betweenness, collinearity. So these are preserved when we have a size change. Angle measure is preserved. So this angle in here, angle A, if it was 45 degrees, then over here it's still going to be 45 degrees. So even though it's shrinking, the angles are going to stay the same. So angle measure is preserved. Betweenness is preserved. So if I had a point between A and C, let's call it D, that same point is still going to be between A and C when we come over to the image. That makes sense. And collinearity, if these are on the same line, like C and B are on the same line, I have a size transformation, C and B are still on the same line. Notice, again, that fourth one that we talked about all the time was distance. Distance is not preserved. That should make sense too, because we're changing the size of this. The distance from C to B is not going to be the same distance from C prime and B prime because we've shrunk it or we've enlarged it. So distance is not preserved in this case. All right, so what do these look like here? If you had to draw it, I'm not going to make you do that, but we need to understand the pictures as we move forward and look at these. So I've got the answers already provided for you, what you would do. So it says draw a size transformation. So if you were given this, here's center C, so pretend that this isn't here. This would be the problem that was given to you. You're given the shape, whatever it is. Here's the center, and the magnitude is 1/2. So what you would do is you would physically draw these lines, each one of these lines to C. You would measure them, okay, and whatever that distance is, you're going to put the new point at half of that distance. So if this distance out here was, say, 10, well, then you're going to measure another distance of 5 right here. Because the magnitude is 1/2, you're going to take half of that distance. You're going to put the new one here. You would do that for all 4 of the vertices, and you would have your new shape after the size transformation. So you can see that done right here. If this distance was 10, I put the new vertice or vertex half that distance, or whatever this number is. If it's a bigger number, then it would get farther away and get larger. And so all of these side lengths now will still be in that same proportion or that same ratio of 1/2. So whatever the top was here, that length, let's call it, just to be consistent here, let's call it 12. Then the new top right here would be 6. But we created that by measuring the distance from each vertex to the center that was given to us, and then applying the magnitude there. In this case, it was half. Real quick, I wanted to show you what it looks like when the magnitude is negative. So again, pretend this was the original. You've got center O. You would measure the distance from here to here. Let's call this 8. And since it's negative, you're going to go on the other side. So you're going to measure this direction 1.5 times. You don't really need to worry about the negative. The negative is just more of a direction here. So you do 8 times 1.5, and that's 12. So it's going to be even farther away. That distance is going to be 12. That's going to be the new vertex, and you would do that for each one of these. You would measure how far it is, and you would put it 1.5 times on the other side. And so you can see the result right here. Each one of these points was translated to the other side of center O at 1.5 times the distance. And so this has increased in size by 1.5. So whatever these side lengths were, let's say this side length was, let's do something easy, 4. All right, so then I multiply 4 times 1.5, and the new length on the other side is going to be 6. And you can see actually where that's going to end up. It's going to flip to the other side here. So those are going to match up. It's 1.5 times the size, and it's on the opposite side of center O because of the negative. All right, we're almost ready to do some problems here. Just trying to get this all out of the way. First section in the chapter, we kind of got to go over a lot of vocabulary and make sure we understand what we're talking about before we can jump into the actual problems. So we need to talk about real quick ratios and proportions. These are things that you've definitely studied in algebra, so this should feel like a review. A ratio is a quotient. Remember, that means division. So anytime we set up a fraction actually is division. 5 over 3 is 5 divided by 3. Okay, 1.6 repeated. Okay, that's an actual division problem, even though we call it a fraction. When we're comparing those numbers and we set it up like this, we call it a ratio. So we could have 5 to 3 set up like this as a ratio. You can set it up as 5 to 3 like this. And sometimes you're even going to see it in this form, 5 to 3. It's just a comparison of two numbers, but it is a quotient as well. You can go ahead and divide that, and that's going to be the scale factor that these are increasing or decreasing by. But we can see this in a bunch of different ways. And so each one of these is called a ratio. And if I have two equal ratios, those are called a proportion. So if this fraction equals this fraction, or this rate equals this rate, or ratio, I should say, then this is called a proportion, and there's ways that we can go ahead and solve those. We'll do that here in a second. As we slide down, we need to just make sure we understand the vocabulary here. What are the means? What are the extremes? And what's the property that allows us to solve for our missing piece here? So in terms of labeling this in your homework, sometimes in the textbook, they're going to talk about first term, second term. Just wanted you to see it right here. They go ahead and label it around like this. That's 1, 2, 3, and 4 when you have a proportion. 1, 2, 3, 4. And there's a theorem that says I can cross multiply, and this is the part you should have done before in algebra. I can multiply the diagonals, a times d and b times c, and the result of those, a times d, is going to equal b times c. Now, we're going to label these the means and the extremes, and you can see them right here. The a times d, those are called your extremes, and the b times c are called your means. I'm not super concerned about like which one's which. I'm more concerned about the mechanics of actually setting these up and solving it. So you're going to multiply the diagonals, and the result is going to be equal to each other. But if you see a question about means and extremes, look back to your notes right here to see which one's which. Okay, so we've spent 12, 13 minutes here just setting everything up. Now let's actually do the math. So if I have these equal ratios right here, what they're saying is this number compares to 5 the same way 8 compares to 10. Now, we're going to use this means extremes property and cross multiply to solve it, but there are other ways around this. You can just look at the numbers and how they relate to each other, and you could figure this out probably mentally. The numbers are easy enough. So if you notice, a 5 compares to 10 the same way x compares to 8. Well, 5 is half of 10, so this number has to be half of 8. So it's 4, and that's true. But it's not always going to be that easy. The algebra can set up all different ways. So let's go through the mechanics of this. The means extremes property says I can cross multiply. So when I multiply the extremes and I multiply the means, the result is equal. So x times 10 is 10x. That has to be equal to the product of 8 times 5, which is 40. All I got to do now is solve this simple equation, divide by 10, and x equals 4, just like we said. So for an easy one like this, you can just look at it and you say, oh, 5 is half of 10, so x is half of 8, it's 4. That's always going to work that way. But as we get into things that don't set up as nicely, you're going to want to go ahead and cross multiply. So when you look at number 2, 12 relates to 10 the same way that this top is going to relate to this bottom. So that's not necessarily one I want to try and reason through in my head. I'm going to go ahead and use this property. This diagonal multiplied is going to equal this diagonal multiplied. So 12 times b is 12b. That's going to equal the product or the result of the multiplication for this diagonal. So if I have a binomial here, two terms, being multiplied by a monomial, one term, it's 10 times this whole binomial. You're going to just distribute it. And you can kind of skip this first step once you get used to it and just go ahead and just multiply 10 times this and 10 times this. But in your notes, I want you to see what we're actually doing here. So the 10 is going to get multiplied times the b and times the 14. So it's 10b plus 140. And you're going to go ahead and you're going to solve this equation now. You have a b on both sides. Quick algebra review. Subtract the smaller one away. 12 minus 10 leaves you a 2b. Still have 140 on this side. So divide by 2, and b equals 70. Okay, and if I went back and plugged this in, so you don't have to, but if you checked it, you'd have 70 on the bottom, and then 70 plus 14. You've had 84 up top. So just so you can see what's going on here, 84 over 70, plugging my answer back in. And if, remember, these are a quotient, these ratios are a quotient, it's division. So if I do 84 divided by 70, I get 1.2. If I do 12 divided by 10, I get 1.2. They're equal to each other, those ratios match. That's the proportion. Okay, and we can use the means and extremes property to go ahead and solve for missing pieces there. All right, to the last page now. We're going to use those skills to actually apply it to geometry, right? That was algebra. Now we're going to apply it to geometry. Let's get this in focus for you. All right, so again, we're looking at a size transformation. When these are given to you in black and white, sometimes there's a lot of lines, there's a lot going on. So I'm going to go ahead and highlight the two shapes that we've got here. We've got the original BCD, and we've got the image of that right here. I know it's the image because it has those markings. So if you highlight those, it's a little bit easier to see what's going on here. The center was A. So the distance from A to B, whatever that was, the distance from A to B prime, or the image of B, is going to be in relation to that. We don't know. This looks like it's been doubled, but you can't assume, right? This looks like it's been doubled, which means these lengths would be twice the size of these. But we got to go by the numbers. We can't just go by the eye test. But whatever this distance is, if you measure this distance right here, it's going to be in the same relationship for all 3 points there. So let's go ahead and label what we've got. They tell you that BD, this distance right here, is 5. They tell you that BC right here is 6. And they tell you that the image of BD is 14. And they want you to find BC. They want you to find this out here. And so if you match this up, I have BD and the image of BD, and I've got the relationship. 5 became a 14. So it didn't double, right? We kind of guessed that it doubled. It actually almost tripled. And that doesn't quite match our eye. Like, that doesn't make any sense. If I've got this, if I tripled it, it's going to be probably farther than that. Okay? But you got to trust the numbers here. Just go by the numbers, not the eye test. So 5 became a 14, so 6 became what? Now, some of you will be able to reason through this mathematically in your head, and you're just going to go ahead right away and you're going to do 14 divided by 5, see how many times it went in, and then times 6 by that number to get this. And yes, that works. But if we're going to use the means and extremes properties, set up a ratio and proportion, what is that going to look like? How do you show your work here? So let's compare our sides here. We're going to compare 5 and 14 in a ratio, which looks like this. That has to be equal to the ratio of this side compared to this one, because they're going to correspond. So 5 compares to 14, the same way that 6 compares to x. It's going to look like this. And we can go ahead now and cross multiply. So multiply these, that's 5x. Multiply these, 6 times 14 is 84. The means and extremes property says that the product of these diagonals, when they're multiplied, are going to be equal to each other. So I can quickly just go ahead and do 84 divided by 5. That comes out to 16.8. And that is this distance out here. Now, those comparisons can be set up different ways. You could have said 14 compares to 5 the same way that x compares to 6. Right? But you need to be consistent. If I'm comparing this to this, then I got to compare this to this. But notice when I cross multiply here, 5 times x is 5x, same result. 14 times 6 is 84, same result. So even though I set this up differently, my cross products here create the Same equation. Another way you could set these up is you can compare the sides in one shape. So you can say 5 compares to 6 the same way that 14 compares to x. Notice, when I cross multiply, 5 is still being multiplied times x, 14 is still being multiplied times 6, and I get the same result. So you just need to make sure your comparison makes sense. There's lots of different ways to set this up, and then the cross multiplying will work. Okay, so let's try a practice one now that you've seen it. As we slide down here, if you're watching this on video, I would suggest you pause the video, try this first on your own, see how you do. Okay, but let's go through this together. I'm going to quickly highlight. Here's the original and the new one. They show you, here's your notation. There was a size transformation of the original triangle MNP, and the result is the image of MNP. K is the magnitude, so they didn't tell you what it is. I do know it's a number between 0 and 1 because I went from a big shape to a little shape. It has shrunk, so it could be 1/2, it could be 1/4, something like that. So based on the numbers that they gave us, we're going to actually figure out what's going on here. So let's label it. MP right here is 12. Let's find the matching one. MP, the image of, right here is 5. And then the other distance they gave me, NP, the original, be careful, don't mark the wrong one. This one is 9. And they want me to find NP right here. So I'm going to set up some ratios, set them equal, which is called a proportion, and I'm going to cross multiply. Just set up your matching sides. Again, like I said, lots of ways to do it. I can say 9 compares to 12 the same way x compares to 5. I can say 12 compares to 5 the same way 9 compares to x. Just make sure your comparison matches up your corresponding sides correctly. So I'm going to go 12 to 5. Those are my matching sides. 12 became 5. So 9 is becoming x. I can cross multiply. 9 times 5 is 45. 12 times x is 12x. Notice it doesn't matter which one you do first. If you said 12 times x and got 12x equals 45, that's fine. If you got 12x equals 45, it doesn't make a difference. You're going to solve this the same way. So I'm dividing by 12 to get x by itself, the same thing I would do right here. So 45 divided by 12, not a perfect number, but it's not a number I need to round. It's a useful number, 3.75, not rounded. That's what I get when I do 45 divided by 12. So that is a good number. Again, I could have set this up 9 compares to 12. This side compares to this side the same way this side compares to this side. X compares to 5. Again, when I cross multiply, I would still have 12 times x, and I would still have 9 times 5. So I would get the same answer. All right, last problem. I know this is a long set of notes right here. So how do we relate this in a quote-unquote real-world situation? Where does this come up? So you have an architect, and they're preparing to build a new wing on a library. And for the owner, they're going to create a scale model of what it's going to look like. So not just a model that kind of resembles, but a scale model, meaning every inch or centimeter of the model is an exact measurement that correlates to the real life wing of the library. So if I measured an inch or a centimeter on the model, it's going to match an exact distance in real life. That's what a scale model is. So they're going to say the base of the model that they're showing the owner or whoever is, I'm going to go ahead and just draw a quick picture, 60 by 100 centimeters, right? So it's small because it's a little model. You could probably just hold it in your hand. But every measurement in this model is going to compare directly to real life situations or a real life distance. And they tell you that the model is 7/135 size of the actual one. So if I knew the actual lengths in real life that the wing was, or even a piece of it was, if I multiplied those lengths by this fraction, 7/135, I would get the actual distance here in the scale model. So you can see 7 is a lot smaller than 135. It's a small fraction, which makes sense. The scale model is going to be much, much smaller than the real life wing of the library. All right, so they want me to find the actual dimensions. So I can't possibly draw one big enough, but let's just clearly show that we've got one. The real life one is going to be much bigger than the model. Again, much bigger than this clearly, but just to show the difference here. So I want to find out what are the new dimensions here. Notice I'm going to give them different variables because they're different amounts. I can't say x and x, that means they're the same number. All right, so 60 is going to become a different number in real life, and 100 is going to become a different number in real life. So 60 centimeters on the model is how many centimeters in real life. 100 centimeters on the model is how many centimeters in real life. So all we have to do here is go ahead and set up some ratios and proportions. Now you don't want to shove all the numbers in at once. You're going to do them each individually. So I'm going to say that 60 compares to the real life measurement x at this ratio, 7 to 135. Now notice how I set that up. I can't just haphazardly put things wherever I want, but I know 60 is going to compare to the much bigger number, the way that 7 compares to the bigger number 135. So that's how this sets up. Go ahead and cross multiply. I've got these numbers here prepared for you. So 7 times x is 7x. 60 times 135, might want to just show that so you know where the numbers came from, is 8100. You're going to quickly solve that. Divide by 7. Let me show you what happens here. So 8100 divided by 7 is this number. A lot of times in real life, we're not going to get nice numbers. So we're going to go ahead and just round this to the whole number here, 1157. So x is approximately 1157, 1,157 centimeters. Okay, so this is 1,157 centimeters. Now, if I'm measuring the wing of a library, am I going to measure it in centimeters? No, probably not, right? That's kind of ridiculous. In America, we're going to measure things in feet. But if we're using metric system, it's going to be in meters. Okay. Centimeters, like a century is 100. A centimeter, there's 100 centimeters in a meter. So if I go ahead and divide this by 100, that's just going to move my decimal 2 spots. So it becomes 11.57 meters. Okay, so 1,157 centimeters, you divide by 100 is actually 11.57 meters, and that's a better measurement for a big wing of a library as opposed to centimeters. But when we're talking about the scale model, we're going to talk about centimeters, not 0.25 meters or something like that. So we do need to be able to go between centimeters and meters. They're nice and easy. Okay, and we're going to do the same thing for the 100. What does the 100 become in real life? So we're going to say 100 compares to y, the same way 7 compares to 135. 100 is going to be a lot smaller than this number, the same way 7 is smaller than this. Cross multiply. So 7y equals, multiply by 100, it just adds 2 zeros. So 13500 divide by 7. Oops. And we're going to go ahead and round that off right there. Now the 5 will bump this up. So I'm going to call this 1929 centimeters. But why am I going to give a measurement 1,929 centimeters? That's how long the wing of the library is going to be. No, I'm going to give you the meters. So divide this by 100, which just moves that decimal 2 spots, which is 19.29 meters. Okay, so setting these up as a proportion, cross multiplying to solve.